let's start by applying linear regression, and in fact, even quadratic regression today, to a situation you should not apply to just for fun. This is just for fun, with data about prime numbers. And I'm going to do it in Mathematica here because it's going to be nice for visualization's sake. Data about, say, the first 5 prime numbers. The first prime number is 2, the second prime number is 3, the third prime number is 5, the fourth prime number is 7, and the fifth prime number is 11. There's our data. List plot, we'll make a scattergram of these data. Actually, I usually call it a scatter plot instead of a scattergram. And if you want the least squares regression line for these data from Mathematica as quickly as possible based on what I've inputted here, the quickest way to do it is with fit. Fit, put the data list name in here, which is just data, then a comma, then 1 comma x to emphasize you want a linear combination of a constant function 1 and a coefficient of x, the function x, and you do want the variable indeed to be x. There we go. There is our linear regression line, our line of best fit that we found last time for these data. And you can combine the graphs if you like. List plot again plots the data, and then I can plot this function here, -1 plus 2.2x, x going from, say, 1 to 5, and see that it's a reasonable fit for the data. We saw this with the spreadsheet before. It's following the general trend of the data. Now, again, prime numbers don't follow a linear trend, so this is a bad application of linear regression. I'm doing it just for fun, okay? You might wonder, does a quadratic function fit it better? We'll try that. But besides visualizing this, what else can we try to visualize? We can try to visualize the function SSE, right? Remember that function from last time? It was a function of, say, the unknown intercept and the unknown slope. What was it? SSE stood for sum of squares of errors. Sum of squares of residuals is another name for that, but there are other words that start with R in this context, so we kind of avoid R here. And we use E for error, error synonymous with residual. It's actual value minus approximation for each data point squared, and then add those up, sum of squares of errors. Actual value for the first data point, the first prime number is 2. What's the approximate value? It would be b0 plus b1 times 1, because that's the first prime number. That's why I have a 1 there. That's got to be squared. Then add similar kinds of terms. I'll copy and paste to save some time. Make appropriate changes. The next prime number is 3. The next one's 5. The next one's 7. The next one's 11. X increases from 1 to 2 to 3 to 4 to 5. Get rid of that last plus sign. There is SSE as a function of 2 variables in a form that is kind of nice to differentiate, like we did last time by hand. You can expand it as well to see it in an expanded form. That's kind of nice too. And yeah, if you use capital D in Mathematica to do your differentiation, there's the derivative. Maybe we want to expand that. That'll simplify it. And that's the derivative with respect to b0. The derivative with respect to b1 looks like that. And setting those equal to 0 and solving for b0 and b1 is what we do to try to maximize, or excuse me, minimize SSE. We're trying to minimize the sum of the squares of the errors. That's why it's often called least squares linear regression. You might wonder where the word regression comes from, and that's got kind of a sad story, but I won't go into it. Anyway, b0 is -1, and b1 is 11/5. In short, it's like some discrimination is the background of the word regression. b0, the intercept's -1, and b1's 11/5, right? 2.2. That's matching what we got with fit. -1 and 2.2. Can this be visualized in some other way than this picture here? Sure, I can graph SSE. I can do a plot 3D, SSE, B0, B1. Probably want to pick a value of B0 close to -1, like -2 to 0. And a value of B1 close to 2.2, like 1 to 3, say. There we have it. Maybe we want to restrict the plot range a little bit more in the vertical direction. Let's also evaluate SSE at -1, 2.2 to see how low it goes. 2.8 is its lowest value. So maybe make the plot range go from 2 to 5. A little bit strange, but it does look like it has a minimum where we said it has a minimum. If you wanted to rigorously verify that it's a minimum, you could use, there's a second derivative test in this multivariable case that involves computing a bunch of second derivatives and computing a determinant of a certain matrix. We won't go into that. It is a minimum, okay? What about if I was after, okay, I think, well, okay, a linear fit's no good, but it does sort of look like these data points could follow a parabola more closely. Maybe I should try a parabola fit. I could still use fit with data, but then instead of putting 1 comma x, I'd put 1 comma x comma x squared to say I want a linear combination of those 3 functions, x still being the variable, and now I get a quadratic function. And that evidently would be the quadratic function of best fit for these data, the least squares quadratic regression. Plot this function. Get rid of a lot of those decimal points. That's some weird approximations going on there. Let's just simplify it here. Okay, pretty good. Looks like it's doing a pretty good job, right? Can it predict the next prime pretty well? Mathematica, or I should say quadratic regression. What is the 6th prime? 15.26? No, it's not supposed to be 13, isn't it? That's pretty far off, actually, compared to how good it seems to be doing here. Yeah, quadratic regression doesn't work either. And it's a bad fit as you keep going. You could try a cubic fit, data 1 comma x squared comma x cubed. See how that does. 0.6. I mean, this is sort of fun, but it's not a good idea. I mean, it's a pretty good fit, but once again, if we evaluated this at x is a 6, it's not necessarily going to do a great job at predicting the next prime. Okay, it's even worse than the quadratic case. Okay? But this can be done, and it can be thought of in terms of, yes, close to 17. It can be thought of in terms of SSE. I'm going to define a new SSE, say for the quadratic one, to be similar to this old SSE, except what? Where is it? Where is it? Where is it? Up here. Except I need plus B2 times 1 squared and 2 squared and 3 squared and 4 squared and 5 squared as well. Like this. I'm using a quadratic function to estimate these things. Right? Still the same prime numbers, 2, 3, 5, 7, and 11 are the actual values. The approximations are coming from quadratic functions, plugging in 1, 2, 3, 4, and 5 into this. And once again, I could take some derivatives. I'm going to do it all in one line here. Of a multivariable calculus function of 3 variables. Get 3 partial derivatives that I got to set all those equal to 0. And solve for B0, B1, and B2. There they are. Hey, yeah, those look familiar. Yes, it's working. Can this be visualized? Yeah, kinda. What, with plot 4D instead of plot 3D? Where's my plot 3D? Instead of plot 3D, we could have done a contour plot. Although I'm going to re-enter the old SSE. There's the old SSE. Here's a contour plot of it near the point where you got a minimum. These are level curves where the function's constant. The fact that it's dark in the middle is where the minimum is. Can I do contour plot with the new SSE? Contour plot 3D. What will I see? Well, I tried this ahead of time in class, before class, and it wasn't looking as nice as I was hoping it would. Okay, I mean, there's not many. These are level surfaces instead of level curves. And there's supposed to be a minimum. These are surfaces along which this function SSE of 3 variables are constant. They look like a bunch of planes. They're actually not planes. They're really elongated ellipsoids, which are like football shapes. But they're so thin, I think, that you can't tell that they really are that shape. There is a minimum in the middle. These are level surfaces on which this function of 3 variables is constant. And there's a minimum in the middle. The function value gets smaller as you go toward the middle of this picture. But it's hard to tell exactly what's going on. It's not ideal. I think it's real. These ellipsoids are just so elongated in certain directions that we're essentially near the minimum and it looks flat. If we went further in just the B0 direction, maybe we'd see it more clearly. Let me try that. 10 to 10 or something like that. Okay, that's a little bit better. Now we're seeing them to look a little bit more like ellipsoids, you might say. Maybe also the B2 direction. Okay, that didn't help. Okay, anyway, the idea is for this kind of function, you can visualize it with level surfaces. The true graph is in 4-dimensional space, which you can't visualize, but you can still do calculus, you can still minimize. And this applies for cubic regression and quartic regression and quintic regression. But you can no longer visualize things, but you can still do the math. You can still differentiate, set things equal to derivatives equal to 0 and solve for critical points. It's still something that can be done. But when you take applied stats with Dr. Wetzel, for those of you who will do that, when you talk about chapter 12 and are doing multivariable regression, there's actually a better approach than all that. It involves matrices, so hopefully that'll be nice. It's actually better. It's not quite as hard to visualize. You focus on matrix operations.